Welcome to our SCP-140 walkthrough of the laboratories for week 5. These are 5 different laboratories, 3 of which have to do with the phenomena related to light, and 2 that deal with gravity. Let's begin. So we're headed out here for week 5 assignments. We click on this here. We see there are gravity laboratory investigations and energy and light laboratory investigations. Let's start with the force of gravity. The force of gravity is something that you'll learn about if you read chapter 3 in your text. But one of the ways that you can get some experience with the force of gravity is to do experiments that would actually be impossible for us to do in real life. Here, what we have are 2 gigantic objects that are billions of kilograms in mass. And they're separated by a certain distance apart from each other, some kilometers. That scale is what you need to experience forces that are similar to the forces that you could feel yourself with your own body, let's say, doing normal everyday activities. And so that's what this simulation is going to show. So if I progress to the first question, you'll see a pop-up come through here. And you'll see some options for what you can do. You can change the mass of the different objects that we're doing the experiment with. You can change the distance between the 2 objects. And one other thing that you can do is you can change the size of the objects. Now, normally when you add material to objects, they get bigger and bigger. Not every object behaves that way. In fact, we're going to come across some in outer space that behave somewhat differently than that. But since this is a virtual interaction, what we can do is change the characteristics of these objects and actually make them constant size. You can still change their masses back and forth like this, but now they're always the same size, and I can get them very close to each other, in fact. So that's essentially what we want to do for this lab right here. You're going to be asked a number of questions about this, trying to get large and small forces, seeing what happens as you change the sizes and distances between things, and trying generally to come up with an understanding of how gravity works. You'll read about in the text how gravity is an inverse square law force, which means that as I get further away from something, the force I feel due to gravity is going to decrease, not by the amount that I increase the distance, but by the square of the amount that I increase the distance. And this inverse square law is something we're going to see in gravity, and we're also going to see it in light. So keep that in mind and maybe keep track of it while you're doing this experiment. Our next lab has to do with orbits. And this lab has some detailed instructions that I want you to follow very carefully. As you read through what you need to do in this lab, you're going to see that there are certain things you need to turn on in order to figure out the different measurements and the different scenarios and the different situations that are possible. What we'll be doing is placing different objects next to each other with different masses and seeing what kind of orbits they can experience. So read through these instructions carefully and be sure to always choose the right options in the simulation. The simulation that we're going to be using is going to require us to look as accurately as possible in terms of how things behave in the real world, the real universe. So let's start off here and see what this looks like. First of all, you always have an option of whether you want to do models or scales. A model is something that is representing something real, but could have some things that are changed to allow you to see different phenomena. You can play around with the model if you want, but we want to take measurements that are as close as possible mimicking the real world, the real universe. So we're going to always do our experiments to scale, as though this was actually occurring in the real universe. And there are a few things you need to make sure you turn on every time you do your experiment. First of all, you can see here that since we're to scale the star and the planet, or the various different scenarios you might have. Here's the star, a planet, and the moon. Here's the Earth and the moon. And here's the Earth and a satellite. But each one of these are to scale so that the size of these objects are exactly the right size compared to how far apart they are. One thing we're coming to understand in this class is that things are very, very far apart out in space. And that means that when we actually scale down the sizes of things, yeah, the Earth and the sun are gigantic, but they're tiny compared to the distance between them. So what are the things we want to look at when we do these experiments? Well, we want to look at the mass of these objects. We want to look at the paths that the objects are taking. And we're going to use a grid to keep track of the different locations that things have been and where they're going. In this situation, you can see that the planet is at one intersection of the grid and the star is at another. And I can start running my simulation by pressing play. And on it goes. This is the orbital path that an object that's an Earth mass will take around an object that's a solar mass, given the distance between the two being the same as the distance between our Earth and our sun. So you're actually doing the experiment of setting up our own solar system here. You're going to be asked for information about how long it takes for things to complete orbits. Or you might be asked for information about what different shapes and orientations and directions things can go in, depending on which simulation you use. Here's one simulation. Here's an example of another one. If I start this simulation, you can see that we have the moon and the Earth traveling together. And they're actually so close to each other in the scale that you can't actually tell they're separated. They look like they're going together, but there is motion of the moon around the planet. We'll go to a different simulation. This is the simulation of the moon going around the Earth. Very similar to that simulation that you did of the phases of the moon, except this is under the influence of gravity. Now, notice there are things I can do, like I can change the mass of the Earth. And if I do, what happens here is I get a completely different orbit. I can even change the mass while the orbit is happening. And if I do that, some very interesting things can happen. Finally, I have simulations like this. This is a satellite about the size of the International Space Station that's orbiting around the Earth. Off we go. In this situation, there's some interesting things that can happen. If I decrease the mass of the Earth, for example, I can get this satellite to do some very interesting things. Different things are going to be asked of you in this situation. You're going to have to be changing the masses of planets to look at different scenarios that may occur. Sometimes you might need to change the scale, and you can do that by zooming out and in over on this side here. So those are the experiments I'm going to ask you to do with gravity. But what about light? Let's look at the experiments I'm going to have you do with light. The first experiment I'm having you do with light asks you to look at the emission of various spectra from atoms and compare it to observed spectra from space. So in this situation, the thing you see that says continuous spectrum, visible light, you can imagine that you pointed your telescope at a star and passed the light of that star through a prism and saw these dark bands showing up. You might wonder what's causing these dark bands. Well, what I can do is I can look at the different spectra that light comes from different atoms, and I can compare it to that continuous spectrum above. And that should tell me what atoms are in the atmosphere of that star. There might be more than one atom in the atmosphere of that star. You're going to have a bunch of them to do. These are a bunch of different spectra coming from different stars in principle. So this is actually something that is done in astronomy. We look at these lights using lamps here on Earth, and we compare them to the absorption lines we see in stars from afar. And that fingerprint of the different atoms matches up to tell us what these different stars are made out of. So I think you should enjoy doing this lab, or at least find it to be straightforward enough. I think it's a really fun thing to do because it is something that is really actually done in astronomy. The next light lab that you have to do this week is the greenhouse effect light lab. Now, the greenhouse effect has to do with the absorption and the reflection and the emission of different kinds of light through atmospheres. In particular, the atmosphere of our own Earth, and we'll come to see it's also important in the atmosphere of Venus and in the atmosphere of many other planets as well. It says that you have three different modes: the greenhouse effect, glass layers, and photon absorption. You can access each by clicking on the appropriate tab. And as you read through what you need to do for this lab, you're going to find that different times you need to use different parts of this simulation. So as we run this, it's going to begin, hopefully. And we're going to have our greenhouse effect as something that we can actually simulate. Here comes the greenhouse effect. So this is the main simulation here. And when we simulate the greenhouse effect, what we end up seeing here is that light is coming from the sun. Those are the sunlight photons. And as it hits the Earth, it gets absorbed by the Earth. And then the Earth emits infrared photons, depending on what temperature the Earth gets to. The higher the temperature of the Earth, the more infrared photons the Earth produces. Now, we can look at the different things in the atmosphere that might affect the interaction of light, either coming from the sun or coming from the Earth in terms of infrared photons. And I can change the atmosphere depending on when I want to look at different concentrations of gases in the atmosphere that may affect these photons. Maybe I can look at the atmosphere in 1750, the atmosphere in an ice age, or I could adjust the concentration and change how much greenhouse gas I want to put in my planet. Greenhouse gases are these gases that will absorb infrared light and re-emit it. Now, when it absorbs the infrared light and then re-emits it in all directions, but sometimes it re-emits it down towards the Earth. And that means the Earth is getting extra energy input into it. That increases the temperature of the Earth. This is exactly what we're concerned about when we talk about global warming and climate change. You can do things like add clouds to your atmosphere, or you can change the simulation to slow things down in case you need to take some account of what's happening. You can also do this thing where you view all photons. This is a simulation that's running, and it is actually doing calculations to figure out what temperature the Earth has. And to do that, it needs more photons than you actually are seeing in the simulation. If you look at all the photons at once, it can get confusing. So sometimes people turn that off and just look at a few sample photons. You'll also, at one point, have to use the photon absorption technique in order to see how different gases behave as greenhouse gases. So for example, I can turn on visible light photons and fire them at different gases and see what they do. Or I could use, for example, infrared photons and see what these infrared photons do with different gases. This, I hope, will set you up for these simulations. And you're going to have to run these simulations to try to answer questions related to the greenhouse effect and how temperatures might change here on planet Earth or on other planets, depending on what gases and how much of those gases are in the atmosphere of planets. This is the interaction of light and matter. Finally, we have one last lab, which is called blackbody spectrum. This is an exploration of how temperature and light are connected. Any opaque object that has a temperature is giving off a tremendous amount of light due to the fact that it has a temperature. I can change the temperature of the object by moving this bar up and down as such. And when I do that, I actually give off different amounts of light. The amount of light that I'm giving off at different wavelengths is indicated by this red sloping curve that you see here. And I can zoom in and out depending on whether I think I'm going to receive a lot more of that light or less of it. And I can get some sense for where the light is peaking by including the graph labels and the intensity and all of this information. I can see ultraviolet, visible, and infrared light showing up on my interaction. What I'm doing here is seeing, as I change the temperature of various objects, what kind of photons are produced. And I may have to zoom in a little bit to really see what's going on. I can actually change temperatures all the way down to the temperature of the Earth if I wanted to. That's about 200 Kelvin. That's actually much colder than the Earth. That's about as cold as it ever gets on planet Earth. But then, as I zoom in, maybe I can see exactly where that description lies for my curve here. You can see that actually it's peaking at very, very low temperatures at very, very long wavelengths. There it is. So there's a lot of fun experiments that you can do, changing the temperature and changing the types of light that are produced. This type of light that's produced is called black body radiation. That is because the ideal calculation comes from something that is the color black, which is something that absorbs all light. And if something absorbs all light, that means it's a perfect emitter of light as well. That means it's giving off the absolute maximum amount of light possible given its temperature. And we can see all of these things as we look through this simulation. You're going to be asked to look at different things, such as what wavelength do most of the photons come out at, right? Right here, I've got a temperature of about 2,950 Kelvin, and the peak wavelength looks like it's at about 0.982 micrometers, which is the same thing as 982 nanometers. You should think about that carefully if that doesn't make sense to you, but there's a conversion down there as well. Sometimes you'll be asked what the spectral power density is at a given wavelength. So at this wavelength, we have, for this temperature, a spectral power density of 2.87 megawatts per square meter per micron. It's a weird unit, but really it's just saying that there's a certain amount of light that's coming out at a particular wavelength. And I can look at other wavelengths too and see what amount of light is coming out at other wavelengths at this temperature. Finally, you'll also be asked sometimes to figure out what the intensity of light that's coming from an object might be. And here we have it listed as 4.29 times 10 to the 6. So that's 430, about 4.3 million or so watts per square meter. That's quite a lot of energy being produced by this, this temperature of an object. You're going to be looking at a bunch of these scenarios and trying to think about what this might mean in terms of the color of stars, in terms of what sorts of photons are going to be produced at which temperatures. And in general, this is the phenomena that explains why stars shine and the way that they do. Stars have a given temperature, and they give off the light based on that temperature. So hopefully that's a good explanation of what you need to do in this lab. By the end of this lab, my hope is that you'll have a better understanding of the light that's produced by objects at a given temperature, which is an extremely important understanding to have if you're going to figure out what stars are doing and how most of the energy that we're observing with our telescopes is produced. So that, as they say, is that. I wanted to give you a nice overview and walkthrough of these labs. Hopefully it's of interest to you. We're going to be headed off after the end of these labs into discussions about different objects out in space, starting with our solar system and moving ever outward further and further, using all of the tools and tips and techniques that we've been developing in the class up until now to really understand what astronomy is all about. So try to get some understanding from these labs try to get some understanding from our problem sets. And as we move forward, I think pretty excitingly, we'll have some better handle on the rest of this amazing universe we're going to be exploring. Thanks very much, and I hope to see you around.